Okay, so this is a chapter one, the chemical world. Now, the idea here is that we live in a chemical world. Everything that we look around us is made up of atoms and molecules. So this is the fundamental concept that we are trying to give you in this chapter. That anything, okay, that you look around you is made up of atoms and molecules, and so they are basically chemicals. Okay, so when you try to understand these things around you, or understand your environment or anything, okay, you have to understand atoms, you have to understand molecules, their behavior, okay, in order to know about. Now, so all things are made up of atoms and molecules. So that's the most important idea in a whole human knowledge. So this is told by Richard Feynman, one of the noted physicists who won Nobel Prize and worked at Caltech. Now, how important it is? Important because now that we know about atoms and molecules, we know about the periodic table, we know how the bonds are formed, so we know how the chemicals behave, and that becomes the basis of chemistry. Okay, so these atoms and molecules, atoms, they are the tiniest particles. Now we now know that atoms basically bind together to form molecules. So there are substances that only contain atoms, and we call them elements. And that is what we see appear in the periodic table, 92 elements. Okay, so these atoms can bind together to form what we call molecules. And you can see this example of carbon dioxide here, and these are molecules. So this carbon dioxide made up of one carbon atom and two oxygen atom, and you can get pure carbon dioxide. Okay, you can get pure water. So the molecules and atoms they form pure substances. So if you have only atoms in that pure substance, we call them elements. If you have molecules in that pure substance, we call them compounds. So water is a compound, while hydrogen and oxygen are the elements. Okay. So much of the behavior of this molecule that you see here, carbon dioxide, will depend on its chemical bonding and the shape. Okay, the very characteristic of carbon dioxide. So here we have drawn carbon dioxide as a straight line. Okay, yeah, so as if the carbon and oxygen are joining like in one straight line, but you might have other molecules like water, which are angular. Now that very shape, changes the whole property of these molecules. The carbon dioxide is a gas and water is a high boiling liquid. And so as we learn our chemistry, we'll also be able to, predict this kind of characteristic ourselves. And you can extend that idea to larger molecules, okay, like proteins, receptors on the cell, how drugs bind to the receptor, drug actions, and so on. And so at the core of all this, whenever there is interactions, so life itself, depends on interactions, okay, chemical interactions. And when you think of how everything is getting controlled in our body, how our body is keeping that homeostasis in the blood, that is from molecular recognition. Okay, how a drug works through molecular recognition. So there is nothing you can hold or touch that is not made of chemicals. So it's basically the world around us is made up of the chemical. We are living in the chemical world. And if you look at this uh, picture, so everything like your soda, if you look at the soda, it has carbon dioxide, it has water, it has the glucose molecule. The glass itself has its molecules. Now these are compounds. Okay, water is a compound. Your glucose that is contained there is a compound. But if you look at the tip of this pen, which is steel, so this is an element. It contains only one kind of atoms, iron. Okay. Now, the molecules can be small like water, carbon dioxide. It can be huge like your DNA. So the cell contained in this hand, it has DNA, single molecule. Okay. like a meter long, but it's still one single molecule. Amazing, right? So the our world is made of chemical world. So in order to understand this world, we devise methods. So from this chapter, these are the crux of this chapter. What is scientific method? So that's the question we'll get. So scientific method is a way of learning that emphasizes observation, experimentation to do what? To produce knowledge as a result of the senses. So you are collecting data, you are analyzing it, okay, and trying to make a sense out of it. And even when you are watching like the rising of the sun and the setting of the sun, that's an experiment, that's a scientific method. And it has to be done methodically. You have to keep and watch, like a clock, to keep time when the sun is rising, when the sun is setting, okay, which time of the month, okay, which time of the day. So all this, when you watch minutely, and when you watch all other heavenly bodies, what you get is this astronomical calendar, okay, that we used to use to keep our date time, predict when to when to sow our crop, and when the rain is going to come, and that is important for the country's economy. And that's why every civilization had the calendars, and those calendars were done based on the cosmic calendar by watching the heavenly bodies, and those are scientific methods. Okay, now so when you observe, and this slide is basically the summary, or if you know only this slide, that's good enough. Okay, so observations, you're measuring, observing. So your measurement needs to be accurate. Okay, so there is accuracy and precision in your experiment. That basically determines whether your whatever you are trying to say is believable or not. So observation data keeping is very, very important. Now after doing the observations, you make an hypothesis. So there are three things here: hypothesis, law, and theory. And you will get questions out of them. And the questions are very simple. What is a hypothesis? What is a law? What is a theory? And given an example, we have to say, is this a law? Is this a theory? Okay. So let's see what they are. So hypotheses are tentative interpretations of the of these observations that you are making. Okay. So that means you observe, that's your own experiment, and you are trying to make some sense out of it. You're trying to predict something, and that's your hypothesis. Okay. Is a tentative interpretation of your observation. When many people, observe similar thing and try to summarize that, that's a law. So law is a summary of large number of observations, usually thousands and thousands, done by many different people at many different parts of the world. So, like if you see uh, that the sun rises in the east and sets in the west, if you are the only one watching it, then it's an observation. So you can make a hypothesis about how the Earth is rotating. Okay, uh, but but that's the explanation. We'll go to the explanation later. But the fact that the sun rises in the east and sets in the west is an observation done by you. Okay. Now, if this is observed by many different people, thousands and thousands, and you summarize that observation into what you call a law, always rises in the east and always rises in the west. Okay, that's a law. Another example can be like if you are, uh, you know, doing a chemical reaction with A and B and get C, you will see that the mass is always conserved. There's no change of mass. Now, if you was if you do it with several substances in your lab, you can basically that's observation. But if many different people see the same thing and summarizes it and says, okay, whenever you do a chemical reaction, okay, matter is always conserved, mass is always conserved. That's a law. It's a summary. But when I'm saying that, I'm not trying to explain anything. The explanation is done by the theory. So theory explains the law, and that explanation, maybe, uh, uh, you know, may be correct or maybe a hypothetical one. Like when Einstein gave his theory of relativity, it's called a theory because he tried to explain the observations of the time. And while giving that theory, many of the concepts that he brought forward were not there at all. And he was a theoretical physicist. So somebody has to do experiments to figure out whether what he said is correct, but he showed mathematically on paper that this is possible. So theories can often be like that, doesn't need to be always proven and can get proven later. Okay. Now all these, you know, uh, hypotheses, laws, and theories are tested, validated by experiment, and this cycle is going on all the time. Even after thousands and thousands of years, you will see this cycle of testing and validating and refining. So here is an example of the kind of question you might get. Like classify each statement as an observation, a law, or a theory. When a metal is burned in a closed container, the mass of the container and its content does not change. Law is a summary of many different observations. So do you think that's too many? Just a metal. So that's observation, right? So that's observation because you observed it in your lab that this happened. Now, if you look at uh, when wood is burned, D, let's say D, okay? When wood is burned in a closed container, uh, its mass does not change. It's the same idea. Like the metal, it's the observation. Or whenever you do a chemical reaction, total mass does not change. So is that a law or the observation? I'm saying whenever you do a reaction. That means you are basically summarizing. Summarizing, we are, and when you summarize, you can see the general statement. Okay, and that's a law. And that's called the law of conservation of mass, actually. Uh, so so that's the difference between observation and others. Observation is only for a particular experiment or a small set of experiment, but law is a basic summary of many, many different observations.
Mm.
Okay, if you look at B, okay, so basically that was C, what I just said, that matter is conserved in chemical reaction. Same thing, what I said. So C is a law because matter is conserved. It's a very general statement on matter. Whenever you are doing chemical reaction, mass is conserved. Okay, now let's look at um, B. Matter is made up of atoms. Is
Mhm.
it a theory, a law, or observation?
Yeah.
So law is a summary of many different observations.
Mhm.
Is that a summary of many different observations? Who observed atoms? Have you? No, we never observe atoms. So
Mhm.
this is basically theory. Then,
Theory.
and that's Dalton's atomic theory, because Dalton proposed this theory. He never saw atoms. Nobody of us even saw atoms up to this day. Um, but he said that something like atoms should exist if you have to explain the chemical reactions, if you have
Mhm.
to explain the laws of conservation of mass, and so matter is made up of atoms. That's a theory.
Yeah.
So that's Dalton's atomic. So when you are doing this, all these experiments to do your observations, there are quantifications involved. You have to quantitate, like measure something. So measurements are part of observation and very, very important one. Okay, because your explanation will stand on this measurement. Okay, and how precisely you can do this, will basically make or break your final conclusion. So precision. Now, how to determine our precision and how to measure all this? So that brings us to our next chapter about measurement, and it's very, very important chapter. We'll be using that knowledge that will acquire from that chapter into every other chapters. Okay. Uh, So there'll be numbers, okay, there'll be units in measurement. Now, there's an example here, like why precision? Now we can basically judge from common sense, but how do you judge precision based on numbers? That our next chapter. But like if you look at this example here, two samples of water may feel equally hot in your hand. So if you are, our hand is an instrument, right? We can feel hot or cold. But if you touch something and tell me, oh, this is 41 degrees centigrade and that one's 43, I'll laugh at you, right? And
Mhm.
we know why we are laughing, but we cannot explain why we're laughing. We are laughing because we know that you cannot be that accurate. Okay, right? We cannot be that precise with the hand. Uh, but the correct term is that your precision instrument, the hand, cannot measure the difference of 2 degrees.
Mm.
Okay, so you need a thermometer, and the thermometer, there are different kinds of thermometer, different forms of thermometer. Again, I can say that it is 41 degree, I can say 41.5 degree, I can say 41.0 degree. Okay, that depends on thermometer. Or I can say 41.00 degree centigrade. Okay, so what should I use? That depends on the the thermometer that I'm using. And when you are, let's say, making conclusion about global warming, and you want to say the world has heated up by zero point 0.5 degrees centigrade, in 1 year, which is lot actually. Okay, now zero point 0.5, can you do that with our regular, you know, thermometer that we do use in a lab? No, because the uh, b- amount of error that we have in our reading is not enough to conclude a zero point 0.5 degree centigrade difference. So we have to get something like which is accurate to 0.000 degree centigrade. Okay, or at least two places of decimals of accuracy. We need a more precise instrument, and that should show up in data. So when you're writing on data, writing 41, writing 41.0, writing 41.00 tells the reader, whoever is looking at the data, how precise you are with your instrument. And those zeros that you are putting after the decimal place are significant. And they tell you that you are accurate to second place of decimal when I say 41.00. So there's a difference between 41 and 41.00. Okay, and that is what you're going to learn in the next chapter. It's almost like, there's this joke, and you might have heard about this. Okay, so there's an advertisement that came up. The museum advertised that there's a fossil under in display, which is a million years old. So a kid went to the museum to see that fossil, and there's an attendant standing in front of it. Okay, and he asked the attendant, "What is the age of the fossil?" And the attendant said, "It's 1,000,002 years." And the child, 1,000,002 years, he's a child, so probably in the elementary school, but that it still did strike him. How could you be that accurate? Okay, and the attendant said, uh, you know what, when I I'm running out of battery. Hold on. So when I first joined this in a museum 2 years back, my supervisor told me that this fossil is 1 million years old. Now I am working here for 2 years, so this must be 1,002 years old.
Oh.
So, so what is the problem with that statement? Now we all know that that can't be correct. The problem with the statement is when you measure that 1 million year for that age of the fossil, there is so much of error in that 1 million year that my 2 year addition, will not make a difference. So even our calculator will do stuff. Okay, it'll add 1 million with a two. It cannot make a decision, but we make a decision. Okay, that this addition cannot be correct. It's like adding one drop of water into a bucket of water and say that this is one bucket and one drop. Okay, no. So there's one thing that is you can add, multiply, subtract in the calculator. Another thing is to make the correct decision that what size I should take. Like if you are dividing 10 with a 3 or the 11 with a 3, the calculator will give you never ending digit 3.333 something or 3.6666 something. Okay. And if your calculator is big enough, it will never end. Okay. There's a recurring numbers. Now, so how much should I take? Now, on a good day, if I'm happy, okay, I'll say, okay, let's take 5 decimal places. And on another bad day, if I'm not in a good mood, I'll say, okay, let's take 1 decimal place. Now, we cannot make decisions like that. So there must be logic. When the calculator is dividing, it is just dividing. But we have to look at the reality that how accurate my instrument was when I measured that 11 and that 3. Okay, and my answer cannot be anything over that accuracy. So by dividing, I cannot make it more accurate. So I have to limit my answer depending on what instrument I started with. Okay, the accuracy that I started with, and that those techniques we learn in the next very very important chapter, and you need to practice and practice enough. Okay, so that you are really uh, okay with that chapter so that we can move on to the next chapter. Okay, like other calculations involved and also the lab. And again, so chemistry requires commitment, of course, any subject for that matter. I would not say chemistry alone. You must do your work regularly and carefully. And if you do that, you will succeed and you will be rewarded by seeing a whole new world, the world of molecules and atoms. And also, since many of you will be going into biological science, I would say the life itself. Okay. So this is our, you know, and there are, you must be curious and imaginative. You must be willing to do calculations. You must be committed to learning the material. Do your homework.